would be concentrating would be, capacitors practice problems. And this is the fifth lecture in our capacitance series. So we would start with a quick recap of a couple of things which we have studied in our previous lectures. That is, we would see about, how to solve if a portion of a circuit where capacitors are connected, it's short circuited. We will see or we will work out a practice problem related to symmetry. And then here, once we end our today's recap, we will move into the next set of problems, which I term as redraw. So a particular circuit would be given, and that may look a little complex, but the moment we redraw using the redrawing technique, we would see how that would be very, very simple. So obviously, that is just an illusion. Once we redraw, it becomes a very simple circuit, right? The next one, we would go into Wheatstone bridge. Yeah. So in our previous lecture, we have seen how do we solve, when we have a balanced Wheatstone bridge. So we know once we get a Wheatstone bridge, if it is balanced, so we can very easily remove the middle limb, and then it becomes a very easy circuit solving, right? But when it is not balanced, how do we tackle that problem? So that we will see today. And then towards the end of it, so we know that in our definition of capacitors, we had studied that a capacitor or a parallel plate capacitor is created by taking two plates which have equal and opposite charge, which means if one plate is given charge plus Q1, we give minus Q1 charge to the other plate, and the net charge on the capacitor we take as Q1, right? So, which is common. So, we would see that if that is not there, will it be a capacitor? If yes, what will be the capacitance? If not, why? So, we would understand why does the definition stands that if charge plus q and minus q are given to the both the plates of a capacitor, why do we actually take the net charge or the effective charge on the capacitor to be q? So we would understand all those things today. So without wasting further time, let's jump into our today's practice session, and let's see all these one by one. So let's get started with the first one related to short circuit. Okay, so let's draw a circuit and we'll see how we would solve it. Okay, so say this is my given circuit that I have a capacitor here, there's a capacitor here, there's a capacitor here, there's a capacitor here, there's a capacitor here. Okay, so we have seen this geometry in our previous lecture also. So where all the capacitors say were 3 microfarad each, 3 microfarad, 3 microfarad, 3 microfarad, 3 microfarad, and 3 microfarad. Okay, so this was already there. Now what I'm gonna do in the previous practice problem, I had only short circuited this in, and today we would see how will it change if I short circuit this entire stuff. Okay, so we know that short circuiting means when there is a zero resistance path. So because this is a zero resistance path, right? So the ends where it is starting and ending. So this entire piece is short circuited. And we have studied in our previous lecture also that in a circuit, if you are finding a limb as short circuited, that portion of the circuit does not contribute to the effective capacitance or resistance or inductance in an electrical circuit. Okay, which means those things can be safely removed. And that's why, because we have given a short circuit across these 2 points, So obviously, this capacitor is useless. This capacitor is useless. And also, this capacitor is useless. Now, obviously, if all these capacitors are useless and I remove all these, so how would my circuit look like? So my circuit would look like this, that I have one 3 microfarad capacitor here, one georesistance path, and another 3 microfarad capacitor. Okay, so obviously, as this portion is short circuited, I can safely remove all these, and that is why my circuit has been reduced to this. Now, when my circuit is reduced to this, now this is very simple. So if you see, we can now apply the lovers couple rule here, that this is their, junction point, and at that junction point there are two and only two capacitors. There is no third, disturbing element. So obviously that means this 3 microfarad capacitor, first one, is in series with the other 3 microfarad capacitor. So obviously our equivalence capacitance C equivalent is nothing but A is nothing but 3 by 2, right? So we know if there are n number of capacitors connected in series, then the equivalent capacitance becomes C by n. So obviously the C equivalent becomes 3 by 2 microfarad, and that is the answer. Okay, so while solving short circuiting, just keep a tab that across which 2 points the circuit is, or which limbs are getting short circuited. So remove those things from the circuit, and circuit would be very easily solved. Okay, and again, we are not doing it, forcibly. The fundamental reason is when when a portion of the circuit is short circuited, those elements do not contribute to the effective electric circuit. So that's why we remove, be it resistors, be it capacitors, or be inductances or inductors. We will remove those electrical circuit equipments because they are effectively not contributing at all to the electric circuit. Okay, so you may quickly note it down, and while you note it down, let me start, giving or writing down the next circuit which we will solve, and that is a little more interesting. And again, as I said, the first two will be recap. So we studied this thing earlier, and the next one is also related to some symmetry of capacitors. Okay, so let's see what what we are gonna do here. Okay, so say I have a geometry like this. There's one more capacitor here, two more capacitors are say connected here, one like this, one like this. Okay, one more capacitor is here, and then across the diagonals. Okay, so if I put one capacitor here, another capacitor here, and like this. So try to obviously make both the lines, of the same length, or else that would be a cell. Okay, so one more capacitor here and one more capacitor here. Okay, and in this circuit, each capacitor is, having capacitance C, and I want to find out the equivalence capacitance across these 2 points A and B. So this is our next practice problem. How do we solve it? Okay, so students, I told you, in my previous lecture also, that if you are solving it in an entrance exam, okay, I would recommend you to, replace this by registers. Okay, so first thing which I'm doing it is only from an entrance perspective. Okay, so replace this with registers. So you have one register here, you have another register. This is the third register, fourth, fifth, sixth, seven, eight, 9, and 10. And I want to find out equivalent resistance across these 2 points. So the same circuit, draw using resistors. Okay, and consider each one is having resistance R. So we know in case of registers, we mentally connect it to a cell. Okay, so when we know that there is no easy way of finding out series and parallel, we first mentally connect a cell to this circuit and we try to distribute currents to the first half. Okay, so say current I comes over here and I1 goes through this side, I2 comes through this link. Okay, now from this, if I1 is going to this side and I2, when once I1 reaches this point, I1 has two paths to follow. So suppose some current I3 came through this side and some current I4 came through this link. Similarly, once I2 reaches this node, this one also has got two possibilities. So say some I5 current goes through this side and some current I6 comes through this side. Okay, now I have reached half portion of the circuit. So I would stop here and then I would mentally or I would reverse the cell. If I'm reversing the cell, so see, if I'm reversing the cell, then I would see the similar things from this side. Okay, so a current I is coming from here and I1 will go here, I2 will go to this side. If I1 is coming here, from here, I3 will go like this, and then I4 will go like this. Once I2 reaches this node, I6 will go to this side and I5 will go to this side. Now I have completed the circuit. But we know we are dealing with DC circuit, that is direct current. We are not dealing with alternating circuit. So which means polarities will not be changed automatically. So which means I would now remove the cell again and I would put the original cell. Okay. Once I am putting the original cell, the second part where I have put the cell oppositely, I would make all the current directions, reverse them. And remember, I would only change the direction. I'm not touching their magnitude. Okay. So I1 rather than going like this, now I'll show it like this. I4 which was coming from right to left, I'll show it from left to right. I3 which was coming from up to down, I'll show it as down to up. Okay. I5 was going towards up, also I5 coming down. I6 was going from right to left, also I6 from left to right. Okay, so now my entire current division is done. After this, I will remove the cell completely. Now, after this, in registers, what we were doing, we were doing a little bit of redrawing. Okay, so if this is a junction point, we know that in electrical circuits we can twist the wires a bit, right? So I can twist the wire like this and I can connect it, so which means effectively I have done no change to the circuit. Okay, now if you notice, I3 current is coming like this and going back like this. I5 current is coming like this and going back like this. Then if I3 came and went back like this, I5 came and went back like this, then in this central segment, in this central limb, what is the current? Current I equals to 0. So if no current is flowing through any limb, I know that I can happily disconnect it from the circuit. And if I disconnect it from the circuit, now if you see, the circuit becomes much easier. Okay, and now we can quickly solve it. So we know these two R's are in series because this is the junction point. At the junction point, there are two and only two resistors. So effective resistance of these two would be 2R. So I can remove both of these, and in this place I can put 2R. Similarly, I can remove these two because these are also in series. I'll remove these two, and in this place I'll put one more 2R here. Okay. Now this 2R and this R are in parallel. So 2R into R by 2R plus R. So that is nothing but 2 by 3R. So I can remove all these and I'll put simply 2R by 3 here. Similarly, here also 2R and R are parallel. So I can remove all these and I can put one 2R by 3 here. Now, R, 2R by 3, all are in series. So what will be the equivalent resistance of these three? R plus 2R by 3, or 3 goes common, 3R plus 3R plus 2R, that is nothing but 8R by 3. So I can remove all these three from the top side and I can put one register 8R by 3 here. Okay. Similarly, from the lower limb also, I can remove all these three registers and I can put 8R by 3 here. Now, these two are parallel, so the equivalence capacitance would be C by 2, your resistance will be R by 2, that is nothing but 8R by 3 into 1 by 2, so it is nothing but 4R by 3. This is the equivalent resistance. Now, the moment you got the equivalence resistance, equivalence capacitance, I said you just reverse it. So it will be 3 by 4C. That is the answer. Okay. So in an entrance exam, I would recommend you that just replace it by registers, find out the equivalent resistance and reverse it. That's how you can find out the C equivalent. But for example, if you get this problem in any of your board exam or in Olympiad, obviously this is not acceptable. So that's why we would now see how we'll solve it if I'm writing in an Olympiad exam or a board exam where I don't want to replace capacitors by resistors. Okay. So the fundamental difference is when it comes to resistors, you can connect cell and electric current will flow through it. So that's why we are doing the current division over there. Okay. And we are removing the limb through which current is not passing. The only challenge with capacitors is the moment it comes to capacitor, you know that there will be a flow of current only till your capacitors are fully charged, right? And that will happen, very, very fast. And after that, there will be no flow of, electric current. So you cannot really say that current is not flowing through a limb, and that's why I'm disconnecting it, okay? But the interesting thing is, what we will do charge distribution, and the limb that would not contribute to charge distribution, we would remove it, because obviously we know that capacitance C equals to Q by V. So if through one limb there is no charge distribution, obviously that would not contribute to capacitance. So for example, I said you the other day also, if you go to market, buy a capacitor, say of capacitance 30 microfarad, until and unless you have actually charged it, it has got no effective capacitance that would be usefully used in any electrical circuit. So first we need to charge the capacitor, and then only it will be able to dissipate charge to the electrical circuit. If you want to tie back this to the original definition, we know that capacitor is an electrical device or electronic device that A, stores charge or stores energy in the form of charge and then dissipates it in a burst to the electrical circuit. So if a capacitor is not storing charge, obviously it will not dissipate that charge to the electrical circuit, and that becomes useless, right? So we will use that same concept here. Okay. So the most important thing here is the charge distribution. Okay. And for charge distribution, we would use a similar funda. We would mentally connect it to a cell. Okay. So say we have mentally connected, and that's why we are showing it with your dotted lines. Okay. That we have mentally connected it to a cell. Okay. Once we have connected it mentally to a cell, we would, say that charge plus Q is coming out of the positive end and charge minus Q is going out of the negative end. In reality, you know what happens, that when a parallel plate capacitor is connected to a cell, so what happens? This negative electrode, your positive electrode would attract electrons from here. Once the electrons come here, because of the chemical, because of your cell operation, it will push the electrons from positive terminal to negative terminal. Once electron reaches the negative terminal, obviously due to electrostatic repulsion, it will reach here. So obviously, if n number of electrons are removed from here, those n number of electrons get accumulated here. So that's why if this end is positively charged by Q, this end becomes negatively charged by minus Q. Okay, so we know this is the funda. So all that we are doing is, for calculation purpose, we are saying, let's say the negative electrode is giving charge minus Q and positive electrode is giving charge plus Q. Okay, so your charge plus Q arrives here. Okay, and from here it will get divided. Okay, so say charge Q1 comes to this side, charge plus Q2 comes to this side. Similarly, charge, and there's a reason why we are using symmetry. So obviously symmetry is pretty important. If once charge minus Q reaches here, if this side we have taken plus Q, then here we'll say minus Q1, and this side if we have taken minus Q2, so here we'll take minus Q2. Okay, now if this plate has got charge Q1, the charge that will be induced on this plate will obviously be minus Q1. The charge on this plate will be minus Q2. Okay. Similarly, charge here will be plus Q1 and charge here will be plus Q2. Okay. Now, if once if you see this plate, and this plate, they are connected together and they are an isolated system. So if I take just these three, right? If I take just these three, sorry, not this one, this and these three. Okay. If I take these three plates, they are constituting an isolated system. And we know the net charge of an isolated system is zero. So if charge on this plate is minus Q1, the total charge on these two would be plus Q1. So say, here let us say, here suppose some charge, your plus plus Q3, and here some charge plus Q4 are appearing, such that Q3 plus Q4 will be equal to how much? Your Q1, because magnitude should be same. Now, if charge here is plus Q3, obviously here it will be minus Q3. Here it will be how much? Your minus Q4. And obviously, once this is minus Q2, and here suppose this is Q5 and Q6. If this is Q5 and Q6, here it will be minus Q5, here it will be minus Q6. Okay, let us do from the other side. Okay, so from Q1, Q3 came to this side, Q4 came to this side. So we'll go with the same thing. So Q1, so this one will be minus Q3, and this one will be, so this one will be minus Q3, and this one will be minus Q4. Okay. The reason is simple. We are going by the symmetry. Okay. Similarly, once Q2 is coming here, right? So once Q2 is coming here, so some charge, this is plus, so which means this and this would get minus charge. So say this one would get your how much? Your minus Q5, and this one would get minus Q6, that we have already written here. Very good. Now, if this one is minus Q3, then this one will obviously be plus Q3. Okay. If this one is minus Q5, this one, okay, wait. So this one is plus Q2, this one is minus Q5. Yeah. So when this one is minus Q5, so this one will be plus Q5. Okay. So if you see here, now here also we can redraw it like this. Okay, so we can redraw it like this. So one moment, sorry. Here it will be plus Q5 and here it will be minus Q5. Now here, if you see, the charge here is, I'm sorry, yeah, okay. So charge that is coming here is just getting distributed to this side. Charge that was minus q5 here, that is getting distributed with plus q5. So if I connect one connector here, effectively this end is not contributing to charge distribution. And if it is not contributing to charge distribution, obviously I can happily disconnect it. Okay, and if I am happily disconnecting it, now it becomes simplified just like your previous case. So see, minus q3 plus q3 0, minus q5 plus q5 0, which means this limb there is no charge distribution, or it's not contributing to charge distribution, and I have removed it. Okay, now obviously now it becomes simpler that this capacitor is in series with this. So C and C. So equivalent capacitance would be C by 2. So I can remove both of these and just put one C by 2 here. Similarly, I can remove these two. These two are also in series. This is the junction point. At the junction point, there is no third disturbing element. So it would also be C by 2. Okay, and now C by 2 and this C, these are in parallel, so obviously this would be C by 2 plus C, that is nothing but 3C by 2. Okay, similarly this one will also be, now these two are also parallel, because again by taking those two we are able to complete a loop. So we can remove both of these and we can put a simple 3C by 2 here, right? Now if you see this 3C by 2, okay, this one, and this one, all of these are in series, right? So C is C by 2, and this is your 3C by 2. So C by 2 into 3C by 2 by C by 2 plus 3C by 2. So that is nothing but, in numerator we are getting 3C squared by 2 divided by, in denominator we are getting, so this one will be C plus 3C is nothing but 4C. So 2 cancels out, 1C cancels out, so this is nothing but 3C by 4. Okay, so 3C by 4. So this lower part is now nothing but 3C by 4. And similarly, your upper side will also be how much? 3C by 4. Now, both of these are in parallel to each other. Once these are parallel to each other, you can add them. So 3C by 4 plus 3C by 4, that is nothing but 4 goes common. 3 plus 3 is 6C. So once you divide them, so this becomes 3 by 2C or 3C by 2. Same answer, right? So that's why whenever you are getting capacitors, okay, from an entrance perspective, if you want, you can remove them, or you can replace them by resistors, and then you can always after finding the final answer, you may just reverse C and R. That's it. But in a board exam or an Olympiad exam, you may follow this process, and this is how you can solve for equivalence capacitance when there's a symmetrical circuit. Okay, now let's move on to the next one. Let's move on to the next one. So next one, or next couple of examples we would see related to redrawing. Okay, so this pattern we will do redraw. So a circuit would look complex initially, but once we redraw, it would be very easy. So let me pick up the examples that I have chosen. So yeah, so this is the first one. Okay, so here is one capacitor. There is another capacitor. There is another capacitor. There is another capacitor. Four capacitors are connected like this, and a fifth capacitor is connected like this. Okay, such that suppose this one is C, this is 3C. This one is C, this is 3C, and this one is suppose your 4C. Now, and it is asking you to find out the equivalence capacitance across these 2 points, A and B. Okay, A and B. Now, in this problem, I have one wing coming here. So, can I say that? So, let's do one thing for simplicity of understanding. Let us give some names to these nodes. Okay. So, let me say this one is P, this is Q, this is R, this is S. Okay. So, I've just given names to the nodes. Okay. Or names to the points. Okay. Now, in this circuit, can I say that the limbs on the QR and QS are they short circuited by this limb? The answer is no, because if you see, it's not a pure conductor. What I have given? I have given a capacitor here. So don't think that the moment you see something like this, it is short circuited. Okay. So if there is a capacitor or a resistor, then obviously this is not being short circuited. Okay. So short circuiting means you should have a zero resistance path only. So which means I cannot remove these two and I cannot solve it. Now what would I do? I will just do a little bit of redrawing. Okay. So we know in an electrical circuit, so suppose this is my electric bulb, okay, and this is my cell. If I change this circuit like this, right? So if I just show this circuit like this, I'll put it like a triangle, okay? So here is your electric bulb, and like this, and I put it the cell here. So obviously these two are same. I've just changed the geometry and nothing else. Similarly, what I would do, I would take this last link, okay, this last link, and I would just flip it inside. So if I'm flipping it inside, so this is how it will come. But if you see, I have not changed any of the nodes, okay? I've just, flipped it inside. So which means my circuit is not changed, okay? I repeat, initially my circuit was like this and I flipped it inside. So obviously my new equivalent circuit is this one. Now, once this is my new equivalent circuit, obviously you can see that this is a balanced Wheatstone bridge, right? So C by 3C, C by 3C. So obviously now it's a balanced Wheatstone bridge, which means I can remove the central limb. If I can remove the central limb, then let's go ahead and remove it. And obviously, once I remove it, it becomes a very easy problem. So on the upper side, this one and this one are in series because at point Q, there are two and only two. So as per the lovers couple rule, they are a happy lovers couple and they are in series. So which means the equivalent capacitance on the upper half is 3C into C by 3C plus C, that is nothing but 3 by 4C, right? So I can remove both of these and I can just put 1, 3C by 4 here. Similarly, in the lower half also, these two are in series and same numbers. So I can remove both of these and put one simple 3C by 4. Now, obviously, these two are parallel because they are a happily married couple. By taking these two and only these two capacitors, you can complete one loop. So once these two are in parallel, so your C equivalent is nothing but 3C by 4 into 2, or 3C by 4 plus 3C by 4, as they are in parallel. So that is nothing but 3C by 2 answer. Right? So remember, students, that sometimes in electrical circuits we may need to redraw. So they would intentionally create a you can say a visual illusion. Okay, so you just need to solve that visual illusion by redrawing it. Fair enough. Now let's move on to one more problem related to these visual illusions. Okay, we saw one in our last class also, and we are seeing few more today. So next one is, yeah. So I have got a capacitor like this. I've got a capacitor like this. I've got a capacitor like this. Okay, these are my points A and point B. Now, what am I doing? I'll connect. I'll connect. Okay, and these are my three capacitors. And the problem is, just a moment. Let me just quickly refer the problem so that, yeah. So I will start one from here, and I will connect one capacitor like this here, okay? And then I would connect one more capacitor like this from here, okay? Now, just for understanding, let us give names: 1, 2, 3, 4, 5. Obviously, the naming is up to you. So in whatever order you want, you can name them. And let me give names to these nodes. This is point P, okay? This is point Q. This is point R. This is point R. What else do I need? Yeah. This is point S, okay? This is point S. So here if you see, no two capacitors are directly in series or parallel. For example, 1 and 3. The moment you are seeing 1 and 3, Q is a junction point. So can I say 1 and 3 are in series? Obviously no, because at the junction point Q, there's a disturbing element, this fifth capacitor number 5. Similarly, between capacitor 3 and 4, R is the junction point, and we have a disturbing capacitor 2. So obviously none of these are in series. Similarly, if I want to take 3 and 5 and see are they in parallel. So I started from 3, I came to 5. I cannot complete this capacitor because I need 4 also to complete this loop. So obviously these are not directly in parallel also. So if nothing is in directly series or parallel, let us just try to redraw it by taking these 4 points P, Q, R, and S. So this is suppose my point P, this is my point Q, this is my point R, and this is my point S. Okay, so now from P, one plate of 1 is connected. So between P and Q, I have capacitor number 1. Okay, so between P and Q, I have connected capacitor 1. Okay, and here capacitance of each capacitor is C only. Okay, now between P and Q, I have capacitor 1. Similarly, between R and S, I have which capacitor? Capacitor number 4. So capacitor number 4 is actually connected like this, right? Now, let us see between point Q and point R. Between point Q and between point R, I have capacitor number 3. So Q and R, I have capacitor number 3. So this is also done. 1 is done, 3 is done, 4 is done. Very good. Now, the other two culprits. Capacitor number 2 is connected between P and R. P and R. So I'll connect P and R. I'll give capacitor number 2. Capacitor number 2. So 2 is also done. 5. 5 is connected between Q and S. Okay. Okay, so this will also not be possible. So 5 needs to be there between P and S. So, sorry, I think this problem is slightly wrong. So the last capacitor should be between P and S. So once it is like this, then obviously it again becomes a Wheatstone bridge. So when this side by this side equals to this side by this side, and obviously you will be able to remove the central link, and it becomes a easy Wheatstone bridge problem. So sometimes we would end up, doing a bit of redrawing and thereby your problems would reduce into balanced Wheatstone bridge. So as far as your problems reduce into balanced Wheatstone bridge, they become easy. But sometimes the if suppose you have got this as a problem, okay, that say now we are entering into the fourth pattern, that is when the Wheatstone bridge is not balanced. Okay, so say this is one capacitor C and 3C. Suppose this is C, this one is 3C, and here it's reversed. This one is 3C, this one is C. Okay, and suppose the capacitor that is connected here is 4C, and these are the points A and B. So if these are the points A and B, then obviously if you see here, yes, is it a Wheatstone bridge? Yes, it's a Wheatstone bridge. But is it a balanced Wheatstone bridge? The answer is no. Because for a balanced Wheatstone bridge, this by this should be equals to this by this. But here if you see, they are reciprocal. Okay. So whether they are reciprocal, or even if suppose somebody would have given this one as 5C also, even you can take that problem as well. But when it is not a balanced Wheatstone bridge, obviously you cannot remove the central limb, and there it becomes a tricky problem. And now the trick that we are gonna, or the method that we are gonna understand here, you can use that method to literally solve, for equivalence capacitance of any capacitor circuit. Will it be very easy? Probably not, because obviously that's the charge distribution method which will be applying. But yes, solve it step by step. It's just a common sense put together, and no big deal. Okay, so say you want to go with suppose 5C also. Okay, so go by 5, or say this one is suppose 3C and this one is C. So let us see how we will solve this kind of a problem. Okay, so here please note down few steps. Step number one. Okay, once you know that it's not a balanced Wheatstone bridge, do one thing: mentally connect it to a cell, just like we had done in case of symmetry. Okay, so mentally connected to one cell, okay, of say potential difference equals to V. Okay, so suppose your potential difference is V. Okay, once your potential difference is V, okay, whatever is the equivalence capacitance of this circuit, suppose the equivalence capacitance is C equivalent. Okay, we'll use the equivalent capacitance of this circuit is C equivalent. Okay, now what we will do, the next step is, like we have done in symmetry, let a charge plus Q come out of the positive terminal and a charge minus Q come out from the negative terminal. Is it mandated that you should take plus Q and minus Q? No, you can take plus 2Q and minus 2Q also, but obviously those should be equal and opposite. Okay, there are some reasons why we take in the bigger multiples, so that the charge distribution becomes easier. But for simplicity, here we'll go with Q and minus Q only. So say here we will say that positive terminal is giving charge plus Q and negative terminal is giving charge minus Q. Okay, so your charge plus Q came here. Okay, so charge plus Q came out from here, and charge minus Q went up to here. Okay, so charge plus Q will get divided. Okay, so first thing is connect an imaginary cell, right? Second point is, let the positive terminal deliver charge plus Q, and negative terminal deliver minus q. Okay, so once positive terminal delivers plus q and minus q, and you can write that you will also take plus nq and minus nq at your convenience. Okay, now third step that we will do is we'll do the complete the charge distribution. Okay, so we'll complete the charge distribution. Once the charge distribution is completed, right, then what you can do, you can either take any of the loops, okay, at least one loop. You can take multiple loops also. If this were a very complicated circuit, you may be required to take multiple loops. We will use a concept, okay. So we know in physics, potential potential is always a point function. It's always a point function, and it's not a path function. Okay, what does it mean? In this circuit, suppose I start. So let's again give them names: P, Q, okay, R, and S. Okay, if I start from point P, okay, and I go in any, and I suppose go in any direction. I'll start from point P. I'll go in this direction like this and come back here. What will be the net potential difference? Potential difference V will be zero, because we know potential is nothing but a point function. You start from a point, you go in a path, come back to the same point. The potential difference is obviously zero. So we will use this concept here, that in any closed loop, the net potential difference is zero. Okay, so you can choose either this loop. Somebody went in a clockwise direction. Another person says, no, I don't want to go in clockwise direction. I'll go anti-clockwise. Perfectly right. It's absolutely right. There is no hard and fast rule that you should only go clockwise or anti-clockwise. It's completely up to your choice, right? Similarly, someone also says that I will not take this loop. I'll traverse through this loop. In this loop also, someone either may traverse like this, or someone may traverse like this. In whatever way you want, you can traverse like that. Okay. So that is the fourth point. Okay. So in fourth point, we'll say that right equation, traverse. Okay. So traverse through any closed loop, closed loop, and obviously write the equation, for potential difference equals to zero. We'll see while we are solving this problem. Okay, so the net potential difference is obviously zero. Fifth point, fifth point, what we will do, traverse from the negative terminal to the positive. So just see here, we just told that, or we just discussed that potential difference is a point function. It's not a path function. So which means if the potential difference provided by this cell is V, so which means your positive terminal minus negative terminal potential is V. So it does not depend whether I'm going from here to here. So when I go from negative terminal to positive terminal of this cell, I will have the potential gain equal to V. Similarly, rather than going through the cell, if I go in the circuit also, so in the circuit, start from the negative terminal of the cell, okay, choose any path you want. Suppose I want to choose this path, okay, choose any one path and traverse up to the positive terminal and write down the equation. So if I went from negative terminal to the positive terminal, obviously potential difference is not zero. Potential difference is equal to the your potential difference provided by the cell. So I should write, I will traverse from negative terminal through choosing any one path in the circuit up to the positive terminal, and the potential difference would be V. So I would write that. So The next thing that we'll do is traverse traverse from negative terminal of the cell through any path. Remember, any path. I can choose any path. Somebody went to this one. Somebody said, no, no, I don't want to follow this. I'll start from here. I'll come up to R. I'll go to Q. I'll come to P. I'll come to A. I'll come here. Perfectly fine. Someone says, no, I will go up to point B. I'll then go to, your R. Then I'll go to S. I'll go to Q. I'll go to P. I'll come back. These are all fine. But you should only notice one thing. You should not come back. Okay, so say you should go to B, R, you went to S. Then again, don't come to your R and start going to a different direction. Okay, so just complete one path throughout the circuit. Okay, so traverse from the negative terminal of the cell through any path in the circuit up to positive terminal and write the equation potential difference equals to V, where V is nothing but the potential difference provided by the cell. Okay, so by using these 5 steps, okay, by using these 5 steps, we will solve and the last thing that we will do, step number 6. Okay, step number 6. So let me write step number 6 here. I hope you would have already noted down the other points. Step number 6. Now, imagine the entire C equivalent of this, if it had been C equivalent, right? So can I say C equivalent will be nothing but so we know Q equals your capacitance C is nothing but Q by V. Okay, so which means your C equivalent is nothing but Q by V. We'll just use it and find out the value of C equivalent. Okay, so we'll use that last trick here. Okay, so let's see how do we use it in this problem. So let me erase it. I'll draw it again, and then we'll see all the steps, and then we'll arrive. Okay, so now let me redraw the circuit. So I had one C here, one 3C here, one 3C here, one C here, and one 4C here, 4C, C, 3C, 3C, C, and these are my points A and B. Okay, so as we said, point number 1, let us first mentally connect a cell. Okay, if I'm mentally connecting a cell, and suppose the potential difference was V. Okay, so say here charge Q is appearing. If charge Q is appearing, okay, so obviously suppose charge Q1 or positive Q1 appears on this plate and positive Q2 appears in this plate. Okay, or I can write if this is Q1, right? So this one will be how much? This one will be nothing but your Q minus Q1. Okay, okay. So Q minus Q1 charge will appear here. Okay. Now this is done. So if charge plus Q1 is here, so here it will be minus Q1. Okay, and here if it is Q minus Q1, so obviously in this plate it will be opposite of that. That is nothing but Q1 minus Q. Okay, now let us see from the other side. From the other side, charge minus Q came here. So if minus Q is coming, suppose this one gets charged. Okay, yeah. So if you see here, towards the capacitor of capacitance C1, we have sent charge Q1. So which means here this will be minus Q1. So this symmetry you need to keep a tab on. If you send minus Q1 charge here, obviously your charge distribution is wrong. So you will end up getting a wrong answer. So say minus Q1 comes here, and if minus Q1 is coming here, obviously how much charge will go here? So here charge will be, so here charge will be how much? Your minus Q plus Q1, right? So obviously minus Q plus Q1 minus Q1. So Q1 gets cancelled minus Q. So so the addition is minus Q. Perfect. Okay. Now here if it is minus Q plus Q1, so what will be charged here? Here this one will be obviously the negative of this. So this will be Q minus Q1. Okay. And here if it is minus Q1, here it will be plus Q1. Okay. Now only this one last capacitor is left out for charge distribution. So here what we will do, we will go by your basic rule, right? So we know that if if you see this capacitor, and this capacitor together, they are forming an isolated system. So obviously charge here will be how much? Equal and opposite to the addition of the other two, because net charge has to be 0. So here charge is minus Q1. Here it is plus Q minus Q1, right? So if here it is Q minus Q1, and here if it is minus Q1, so obviously charge on this plate will be addition of both of these, and then we have to reverse the sign, right? So minus Q1 plus Q1 cancels out, so plus Q, which means here it will be minus Q, right? So here if it is minus Q, sorry, yeah, here it is minus Q, and obviously here charge will be plus Q, okay? So which means using this, we have already completed the charge distribution. Once we have completed the charge distribution, we'll go to the next point, that let us choose any one loop, okay? Suppose I want to choose this loop and I want to go in clockwise direction, okay? So which loop I have chosen? So this is point P, this was point Q, this is point R, this is point S, okay? So I'm choosing the loop Q, sorry, PQS. In loop PQS, let me start from point P and I'll come back to point P. You can start from point Q and come back to point Q. You can start from S and come back to point S. It's your wish. But I want to start from point P and I want to come back to point P. Okay. So in loop PQSP, so I started from PQS and I came back to P. So let's go ahead. Okay. Just a moment. Let me drink a bit of water. So yeah. Now. So what is the what? Okay. One more thing that you should remember. Okay. When we are going from the positive end of a capacitor towards the negative terminal, obviously we are going into a potential drop. Okay. So which means the effective potential will be minus. If I'm coming from negative terminal of a capacitor to the positive terminal, then there will be a potential gain, which means I'll write plus, but no positive potential difference gain. Okay. And if it is any other circuit, we'll see accordingly. Okay. Now, if I know capacitance of this capacitor, first capacitor, okay, capacitance of first capacitor is C. Charge on this capacitor is Q1. So can I say your C is nothing but Q1 by, suppose V1, suppose potential difference across this would have been V1. So if potential difference is V1, then I can say V1 is nothing but Q1 by C. So whatever is the charge appearing across this capacitor by the capacitance would give me the potential. Okay, so let me use that formula here. So what would be the capacitance here? It is nothing but Q1 by C, plus or minus. I'm going from positive terminal of the capacitor to the negative terminal, so which means it will be minus. It's a potential drop. I reached point Q. From point Q, I am going towards point S. So and there I encountered this capacitor, which capacitance was 4C. Okay, and here I am going from negative terminal to positive terminal. So if I am going from negative terminal to positive terminal, obviously it's a potential gain. And the charge that is appearing there is how much? Q. So plus Q by 4C. Okay, plus Q by 4C. Now, if it's Q by 4C, I reached point S. After reaching point S, I need to go towards P. So which means I'm encountering this 3C capacitor whose charge is Q1 minus Q, okay? And I'm going from here to here. So here you may have a doubt that, sir, I'm going from a positive terminal to negative or negative to positive. Doesn't matter. If you think this is positive, go with your potential drop. If you think this is negative, go with the potential gain, and automatically your electrical circuit will solve it for you. Okay? So assume that I'm going from positive terminal to the negative terminal, which means I had a potential drop. If I had or suppose for simplicity, let's say that I'm going from a negative terminal to positive terminal. Okay, so which means I had a potential gain. Okay, now if I had a potential gain, so what is the capacitance, or sorry, what is the potential charge on the capacitor by capacitance? Charge on the capacitor is always taken as charge on the positive plate of the capacitor, so which is nothing but plus Q minus Q1, that is charge on the capacitor by the capacitance, that is 3C. And I'm assuming I'm going from negative to positive terminal, which obviously means it's a potential gain. Now I reached point P back. So obviously this much equals to 0. Okay? This much equals to 0. Now let us solve it. Okay? So by solving it, and again, we know Q is divided into Q1 and Q2. So obviously we can say Q is nothing but Q1 plus Q2. So let us eliminate your Q in terms of Q1 and Q2, so that things will be a little easier. Or if you want, you can eliminate Q1 Q2 in terms of Q. Okay. So let us first solve it. So here the LCM comes out to be 4C, and in numerator now this will be minus 4Q1 plus capital Q. Okay, oh sorry, 4C and 3C, so it will be how much? It will be 12C. So 12C will be like the LCM. So 12C is the LCM. If 12C is the LCM, so this one will be how much? Minus 12Q1 plus 3Q plus 4 into this much. So 4 into this much is nothing but plus 4Q minus Q1, sorry, minus 4Q1 equal to 0. So this will get multiplied with 0 and it will cancel out. So that is nothing but, this is minus 12Q1, this is minus 4Q1. So this is minus 16Q1 plus 3Q plus 7Q is nothing but 3 plus 47Q, or I can write it as this much equal to 0, or 7Q equal to 16Q1. Okay, 7Q equals to 16Q1, or this Q I can write it as Q is nothing but Q1 plus Q2, or 7 into Q1 plus Q2 equals to 16 Q1. By solving it further, 7 Q1 plus 7 Q2 equals to 16 Q1, or 7 Q1 goes to the other side, So 7Q2 equals to 9Q1. If 7Q2 equals to 9Q1, then obviously your Q2 equals to 9Q1 by 7. So we will use, so the reason why we are doing it, we are trying to establish a relationship between Q1 and Q2, and we will use it in our next step, okay? And our next step was traverse from negative terminal of this cell to the positive terminal through any path in the circuit. So let's get started. So we'll just keep this one for future use. So let me write it here that your Q2 equals to 9Q1 by 7. Okay, so let us traverse from negative to positive terminal of this cell. Okay, so suppose, and now let me give this also two names. Suppose M and N. Okay, so suppose so obviously I have to travel from here up to here, and let me assume that I want to choose an easy path. Okay, because obviously then your number of variables will be lesser and you will be able to get the solution easily. But if you want to choose any other path, it's completely up to you. Okay, so suppose I'm going from this path. In this path, the first thing that I'm encountering is this capacitor C. And in this capacitor, I'm going from negative terminal to positive terminal, which means there's a potential gain. So how much is the potential? So potential is nothing but charge on the positive place of the capacitor, that is plus Q1 by capacitance, that is nothing but C. So charge by capacitance is potential difference, right? So I reached point S. From point S, I need to go to point this P. So here I'm encountering this 3C capacitor. In this 3C capacitor, initially also I have assumed this is negative plate, this is positive plate. So which means if I'm going from here to here, there's a potential gain. So now, so the potential gain is nothing but charge on the positive plate, that is Q minus Q1 by capacitance, that is 3C. Okay, I reached point P. After point P, there is nothing, and I reach the positive plate of the capacitor. Okay, so that is this much is nothing but V. Okay, now, so can I say that C equivalent is nothing but the total charge that this cell has given Q by the total potential difference, or I can say V is nothing but Q by C equivalent. So I'll just use this. In place of V, I'll write Q by C equivalent, because C equals to Q by V. Okay, now it's pretty easy. So I'll just solve this equation. So this is nothing but I have to solve this part, and here in place of Q I'll place Q1 plus Q2. Okay, so let's first solve this part. Okay, so this is nothing but 3C is the LCM. So this one becomes 3Q1 plus Q minus Q1. Okay, so in place of Q I can write Q1 plus Q2, Q1 plus Q2 minus Q1 that is equal to Q1 plus Q2 by C equivalent, right? So obviously now it's a very simple math. So it becomes, so 3Q1 plus Q1, 4Q1, so 1 plus Q1, 1 minus Q1 gets cancelled out. So here it becomes 3Q1 plus Q2 by 3C equals to Q1 plus Q2 by C equivalent. Now obviously I'll take this one here and I'll take this one here. So that is nothing but C equivalent into 3Q1 plus Q2 equals to Q1 plus Q2 into how much? Your 3C. Okay. Now let's keep solving it further. Okay. So that is nothing but C equivalent equals to, here this is how much? Your Q1 plus Q2 into 3C by 3Q1 plus 3Q1 plus Q2, right? So obviously, oh, this is 3Q1 plus Q2. Sorry, this is not whole, this is 3Q1 plus Q2, okay? So that is nothing but C equivalent equals to your Q1 plus Q2. So Q1 plus Q2 is nothing but your Q into 3C by here 1Q1 plus Q2 is nothing but your Q. So we can say this is Q1 plus 2Q1. So one is Q plus 2Q1, right? Q plus 2Q1. Now, if we want to solve it further, okay, so now it has become multiple variables. Okay, just give me a minute. Okay, so where did we go wrong? So C equivalent equals to Q into 3C by Q plus 2Q1. Okay, so we need to solve this piece. So this Q can be said as, okay, this is 2Q1. So what was our other thing? Q2 equals to 9Q1 by 7. So can I solve it from here? No, the answer is no. Okay, so let me solve this part a little later. So maybe in my next video I'll solve this part. So looks like some I missed out something in the calculation, and now I can't go back and check because I have erased the previous steps. So I'll solve it and I'll show in the next class. So maybe, but this is what we are gonna do. That we will finally use one path from the negative terminal to the positive terminal through this circuit, and then that much will be nothing but equals to P. That is nothing but your what you say Q by C equivalent. Okay, so that is the technique that we need to use. So it looks like some step we have probably not solved correctly, so that's why we are stuck up with this mathematics riddle. So we'll solve it in our upcoming video. Okay, so let's go to the last part, that is if both the ends of the capacitor are not given the same charge q and minus q, then what happens, and why do we have in our definition of a capacitor that the charge on the capacitor is considered to be charge on the positive plate? Let's try to understand that. Okay, so the last part of our today's video, so we'll see that one. Okay, just give me a minute. So say I have created a parallel plate capacitor. Okay, and suppose these are the two plates of the parallel plate capacitor. Area of each of them is A. Okay, the space between them is small d. And suppose we know that in our definition we say we give charge plus q to this plate, charge minus q to this plate, and we say charge on capacitor is plus q, and we say capacitance C is q by potential difference T. Okay, now this thing we have already studied, and we have kind of agreed in the definition. Now let's do a bit of research that if charges are not same, then will it form a capacitor, and what would change in that case? Okay, so say somehow I have given a charge plus Q1 to this plate and a charge minus Q2 to this plate. Okay. So if I'm giving different charges plus Q1 and minus Q2, let's see how will it behave. Now, out of this Q1, obviously, when we are saying, a parallel plate capacitor, the plate will have some thickness, right? And obviously, say, out of this charge Q1 will distribute itself throughout the surface of the plate, right? So some charge will appear here and some charge will appear here. Okay, will it be always same? We can't really say that. So say for example, on this side, on this side, suppose the net charge that has appeared is suppose your, or suppose your on this side the net charge that is appeared is your Q1. Okay, so on this side if the charge is Q1, what will be the charge on this side? This will obviously be your larger Q1 minus small Q1. Okay, okay. Now, if here the charge is plus Q1, so this plate and this plate are placed by a small, or separated by a small distance, and as this is a metallic plate, here the induced charge would be of quantity how much? Minus Q1. Okay, because obviously when two metallic plates are placed close to each other, the charge induced is equal and opposite in nature. So the charge appearing on this side of this negative plate capacitor would be minus Q1. If charge here is minus Q1, what would be the charge here? Charge here will be nothing but minus Q2 minus Q1. Okay, so from this much charge, this much has already appeared here. So some negative charges already appear here. So the outstanding would appear here. So that is nothing but how much? Your Q1 minus Q2. Minus of minus becomes plus. So this becomes plus Q1 minus Q2 charge will appear here. Okay. So now we know that this is the new charge distribution. So let me just highlight them. Okay, so this is plus Q1 minus Q2 minus Q1 plus Q1, and here it is Q1 minus Q. So one interesting thing, if you see here, though we had initially given them different charges, the portion that is forming a capacitor, here if you see charges are again equal and opposite. Okay, but we need to find out that what would be the total capacitance, or what would be the charge distribution in this case. Let us try to understand. Okay, now in this case, if we want to find out the charge distribution, let us consider a point P inside any of these plates. Okay, okay. Now if we consider a test charge P here, we know here there is some positive charge, right? Here there is some positive charge, here there is some negative charge, and here there is some negative charge. So obviously, all these plates would exert some force on the test charge placed at point P, and obviously all of them will have some electric field intensity acting on that point, right? Now what would be the electric field intensity due to this plus charge? So we know electric field intensity due to a plus charge on a test charge is always what? Repulsive in nature. So there will be one charge, there will be one electric field E1 because of this positive charge. Now here there's a plus Q1 electric charge. So plus Q1 electric charge will also give a repulsive electric field in this direction E2. Okay. Similarly, this side of the plate where charge minus Q1 is there, it would pull the test charge towards itself. So there will be an E3 that is due to this charge. Okay. Similarly, here you have another negative charge. So which means there will be one more E4 in the same direction due to charge appearing on this plate. Now, let us remember what was the formula for electric field intensity of an infinitely charged body. It was nothing but E equals to sigma by 2 epsilon naught. Okay? So sigma by 2 epsilon naught, or that is nothing but charge per unit area by 2 epsilon naught. Okay? And now we will just use this formula. Okay? And again, inside any conducting surface, what is the net electric field intensity? That is nothing but zero. Okay, so obviously, as net electric field intensity inside a conductor is zero, so we can say that the vector summation of all these, so E1 vector plus E2 vector plus E3 vector plus your E4 vector will be zero. If the vector summations are zero, we already know that which one are acting, in same direction and which one are acting in the opposite direction. So we can quickly solve it, using our vector symbol. That in this case, magnitude of your E2 net force towards left is E2 will be equal to how much? E1 plus E3 plus E4. So let's find out. So E2 was your electric field intensity due to charge q1 or charge q1, so that is nothing but q1 by 2. And that's why if you see, we have taken area of everything as a q1 by 2a epsilon naught, that must be equal to e1 was electric field intensity due to this charge. So here charge was nothing but how much? Capital Q1 minus small q1 by 2a epsilon naught plus what was the value of E3? E3 was, yeah, E3 was due to this charge, your this q1 charge. So that is nothing but q1 by 2a epsilon naught. Okay, and what is the charge due to this part? That is nothing but q1 minus q2. So q1 minus q2 by 2a epsilon naught. Okay, so now let's solve it. So obviously, your if you see in the denominator, all the terms are 2a epsilon naught. So which means I can cancel out all these. Okay, so which means our equation becomes much simpler. So it becomes q1 here, q1 minus q1. Okay, now this minus q1, this plus q1, they will cancel out each other. Okay, so and here this minus q1 is gone and this plus q1 is gone. So what am I left with? Okay, okay, so if I take this one, so that is nothing but 2q1 equals to q1 minus q2, or q1 equals to q1 minus q2 by 2. So here is the interesting thing. If you see, when we are giving different charges to the different what you say electrodes, or sorry, the different positive and negative terminals of a capacitor, the effective charge that comes on the faces facing each other is nothing but the net difference of them by 2. So that is the very reason when one side has got charge plus q and the side has got charge minus q, what is the difference? Q minus minus q by 2. So that's why it becomes your 2q by 2, that is nothing but equals to q. So that is why, students, that when you have similar charges, we take the net charge on the capacitor as charge appearing on the positive plate of the capacitor. Similarly, Similarly, when charges are different, the net charge appearing, or see, only this part is forming a capacitor. Okay, so this part is forming a capacitor, which means the effective charge is nothing but the difference of the charges, charge on the positive plate minus charge on the negative plate by 2. Whatever you get, that is the effective charge in that capacitor. So obviously, our next problem becomes very easy. So here we have seen three things, okay? So if charges are, if suppose I give one plate charge plus Q1 and another plate I give charge plus Q2. So what will be the effective charge in the capacitor? It will be nothing but the difference of your Q1 minus Q2 by 2. So whatever is the difference, okay, that difference by 2, that much of charge would be effectively used in the capacitor. So obviously, now the next question will become even more obvious. If I give both plates a charge plus Q1 and plus Q1, okay, then obviously your Q net is nothing but Q1 minus Q1 by 2, that is 0. So if net charge is 0, it does not work as a capacitor. So obviously, students, if both the plates have same charge, plus Q and plus Q, then obviously somebody is saying Subham, okay, so obviously when both the plates have same charges, then obviously there will be no potential difference. If there is no potential difference, there is no electric field, and obviously it cannot store any charge. So that is why, remember, ideally in an ideal capacitor we give charge plus Q and minus Q to both the plates. Okay, but we also saw that how it would behave when it is not the same. So with that we come to end of our today's class, and we will meet in our next class with the next topic on capacitors, and we will also see where the correction on that one problem where we did some kind of mathematical error. Okay, so we'll see all that also in the next class. Thank you, students. And Savannah Bano, okay, for you, let me type down my mail ID and we can connect on that. Thank you, students.